Okay, so for 45, I did discuss this a little bit, didn't I? Okay, so hopefully we did discuss this a little bit. So at this point, how did we come up with the moment of inertia for weird things? What is that? Is that a raisin? Right. So when we did moment of inertia for an object, when I talked about the sort of the summing of the electric field from a group of charge, the idea was the same. There is a relationship, like there's a physical relationship that describes that thing. So there is a physical kind of relationship that describes the electric field there and how that comes from charge, right? So we know that that thing is E K Q over R squared, right? That is what tells us how much electric field we're going to get from a certain amount of charge. And then in this problem, we should realize that we have charge at different points all down this rod. So then we're going to have to sum up the effect of that statement over the rest of the object, right? That's how we did moment of inertia calculations as well, right? This is, once again, the beauty and power of calculus that you will experience when you go into college is that you can take equations that represent certain physical parameters and then extrapolate them over various boundaries to see to be able to model natural behavior, which is pretty exciting. So that's kind of like a forward look into what you're going to be doing with all this math later. So how would we do that now? So once again, just like we did the differential unit of mass, because that was what determined our moment of inertia, what determines our electric field? A differential unit of charge. So we're going to take some little tiny delta Q, and we're going to say delta Q is what I'm looking for. What was that?
Raisin.
Okay. Man, no more raisins in my room. Okay, anyways. Yes?
The charge is uniform, but the distance is changing.
Yeah, exactly. Okay, actually, this brings up a good point too, because remember when I was talking, I showed you two things. I showed you the coming up with the electric field from a line of charge and the electric field from a ring of charge. The electric field from the ring of charge, we needed to do zero calculus. Why was that?
R is the same.
Right, the distance to the charge never changed. So we could just add up the effects and be done. But now we are trying to add up the effects of something that's changing, and thus we must use integration. Right? So that's the idea there. But good question.
So why are you integrating Q?
What's that?
Why are you integrating Q then?
Oh, I'm not, right now I'm just sort of experimenting, we're seeing what's going on, right? Because what we're doing is, can you come up, because R is different for every section of this rod, I can't just say KQ over R squared.
Yeah.
Okay, so what I need to do is give myself a little bit of Q that I know is at a distance R. So I'm going to create a statement that defines E for a given Q at a distance R. Well, in order for me to get a distance R, I have to make Q really small. Does that make sense?
Yes.
Yeah. So we are using, Richard has a good question. Why are we farting around with this delta Q? We're not integrating over Q. We know Q. But what we're trying to do is we're trying to say I need a really tiny piece of this rod, a really tiny piece of that charge, right? Because that's going to be at a given R. Do you get what I'm saying? Because R changes depending on where you are in this rod. Anywhere from x all the way to the square root of x squared plus L squared. So then we're trying to use that. Okay, very good. My delta Q, and actually, we should take Richard's Q and say, okay, wait a minute. So what does that mean? This delta Q means, and there's different ways to look at that. The way that I generally look at it is like, it's the density of, and if you remember, we did linear mass density, and we did areal density. remember when we were doing moment of inertia, here we're going to take charge density, which is going to be Q over L times some little thing, and in this case, it'll be like whatever, delta Y. The other way to look at this, is to say the ratio of the differential units should be equal to the ratio of the overall measurements. Does that make sense? I'll say it again. The ratio of the differential units should be equivalent to the ratio of the overall units, or overall measurements, dimensions, I guess. So we, for example, I'll just do it instead of gibbering about it. Does that make sense? That's supposed to be Q, not theta. It's not theta with a tail. So what I'm saying is delta Q over delta Y is equal to all the charge over all the length. Right? And whichever way you want to think about this, whatever works best for you. Yeah.
So it's like the charge in the length is equal to like the whole charge in the whole.
Yes, right? Because the ratio should be the same. Because we said the charge is homogeneous, so every section of the bar should result in the same charge density. So I'm taking the smallest density I can find from delta Q over delta Y, and I'm setting that equal to the overall charge density Q over L. That gives me that statement. Then I work up to the statement delta Q equals Q over L times delta Y. So we now have a good representation of our charge. Well, I just need to fit that into my equation, right? And I'm going to say I'm going to be summing this. So E is going to be, I'll take out that constant right away. Well, you know what? Let me not do that yet. E is going to be the sum of K delta Q over R squared, right? And then we can say, all right, I can plug stuff in and say KQ over L times the sum, because those are constants, I can factor them out, of delta Y over R squared. Now, is everybody okay with the fact that R is going to equal the square root of x squared plus y squared? Everyone cool with that? Okay, now why didn't I say L squared? L squared will give me exactly 1 point at the very end of the bar, right? And I want all points on the bar, so I'm going to use y, and then we're going to integrate over y, which is y. We have delta y. That's a lot of y's. Okay, so anyways, we can now say E is going to equal KQ over L, and then now we have the sum of delta y over x squared plus y squared, and that's 1/2. And of course, from there, I can now say E is equal to KQ over L, the integral from 0 to L of dy x squared plus y squared to the 1/2.
Why is it to the 1/2? Yeah, shouldn't.
Isn't it square root?
Yeah, but shouldn't.
Oh, r squared, genius. Thank you. Sorry about that. We can get rid of that because I forgot we squared the bottom. Thank you.
So 0 to L, the limits.
Yeah, yeah. Now, if we plug this into whatever, Wolfram Alpha, and get our answer, actually this one's not that bad, so we don't have to do that. But if you do this, is that the answer? Almost, right? Because what do they ask? What does this problem actually ask for? It actually asks for this in component form, right? So all you have to do is just take that, right? If we take the two sums, if we take the sum, this said this E was equal to KQ over L times the sum of delta Y over x squared plus y squared, right? And then we just need to come up with EX and EY. Okay, well, if we go back here and you see, well, let me not go back there, let me do this. We have this rod like this here, and we're talking about point P. Do you see that there is this part and that part? This is EX, this is EY. EX, that's going to be theta. EX is equal to E cos theta, and EY is equal to E sine theta. And then what is cosine of theta? Right? Do you see that is x over the square root of x squared plus y squared? And sine theta is y over the square root of x squared plus y squared. Does that make sense to everybody? Okay, so all you got to do is then say EX is equal to KQ. We're just multiplying our E times that. KQ over L, the sum of, and then whatever, I'll just put it, okay, what do we have there? Yeah, delta Y. So it's delta Y over the square root of x squared plus y squared times x over the square root of x squared plus y squared. Oh my gosh, I did it again. I keep forgetting to square that bottom, sorry. X squared plus y squared. And then we can go times x over x squared plus y squared. And that is a square root, so haha, I do have that. And then I do the same thing for EY. EY, I'm taking the same base root, everything up to here is the same. And then I just plug in, so I'm just taking E and then plug all of that in at the end. Okay? And then, now you can integrate both things and have a party, la la la, yada yada, whatever.
Go back
Okay, so this turns out to be
the one with the integral.
this?
Yeah.
Yeah. So basically what we have, like this is just how you get this overall electric field, which is going to be some value in between here, right? And it's probably going to be weighted more towards the horizontal because this is closer, so the electric field will be bigger. But we have to, in order to get the thing that we need to integrate, we need to step back to the summation and then put in the cosine and sine terms, then combine everything, then integrate. Does that make sense? Yes, no?
Can you repeat that?
Yeah, this integral right here is just to get the the final vector magnitude.
Okay.
Okay, if we want to get the components, we want to step back to our summation statement, insert the cosine and sine terms, combine everything, and then move forward with the integration for each of our terms.
Because that'll give you the components.
Yeah, because when we integrate each of those individuals, we'll get the components. Okay, questions, anyone? Did that make sense? Hope so. See you tomorrow. Bye.